Hey guys, and welcome to my first tutorial on working through the contents of Core Pure 1. In this video I'll be summarizing everything you need to know on the topic of complex numbers. If you have any questions at any point in the video, be sure to put them in the comments and I'll try my best to answer them. So without further ado, let's get started. Before we even talk about complex numbers, we need to know about imaginary numbers. Whenever you work out the square root of a negative number, you'll get an imaginary number. In this topic, I represents the square root of negative 1. From here we can work out that I squared is equal to negative 1, I cubed is equal to negative I, and I to the 4 is equal to 1. From I to the power of 5 onwards, the result will essentially loop back from the beginning. So I to the 5 will equal I to the 1, I to the 6 is the same as I to the power of 2, I to the 7 is the same as I to the power of 3, and so on. If we were to use algebra to note this, we could say that I to the power of n is equal to I to the power of n plus or minus 4, where n is greater than 4. If we were asked what I to the power of 15 was equal to, we could essentially use this fact to find out that I to the power of 15 is the same as I to the power of 11, which is equal to I to the power of 7, which is equal to I to the power of 3. And from up here, we know that I to the power of 3 is equal to minus I, which means our final answer would be minus I. Something else that you may be asked to do as part of a question is to evaluate the square root of a negative number. Doing this is quite simple, assuming you learnt how to deal with surds at GCSE level. So we're going to try an example here. In this question, we're asked to evaluate the square root of negative 64. To do this, we can split the surd using the multiplication rule and say that it is equal to root 64 multiplied by root minus 1. We know that the square root of 64 is equal to 8. And from up here, we know that the square root of negative 1 is equal to I, which means our final answer is 8I. Let's try another one. Here, we're asked to simplify 3i all cubed. Remember that this is equal to 3 cubed multiplied by I cubed, as the whole 3i is being cubed rather than just the I. We know that 3 cubed is equal to 27, and we know that I cubed is equal to negative I from up here, which means our final answer is minus 27i. Now that we've got imaginary numbers out of the way, let's start to deal with complex numbers. A complex number is made up of a real number and an imaginary number, and is of the form a plus bi, where a is the real part of the complex number and bi is the imaginary part of the complex number. To add or subtract complex numbers together, you separate the real and imaginary parts and add or subtract them separately, just as it would be in simple algebra. If we have a question asking us to take 2 minus 5i and subtract 5 minus 11i from it, we would separate the real parts to say that 2 minus 5 is equal to minus 3, and then separate the imaginary parts to say that minus 5i plus 11i, as there's a double negative here, is equal to positive 6i. You may also be asked to find the roots of a quadratic equation with complex roots. Now there are many ways to do this, but I'm going to cover two methods you should have learnt during your GCSEs. Let's say we have a quadratic equation, z squared plus 6z plus 25 is equal to 0. We can work out that this quadratic equation has complex roots as the discriminant is less than 0. Remember that the discriminant for a quadratic equation of the form az squared plus bz plus c is equal to 0 is equal to b squared minus 4ac. Now in this case, a is 1, b is 6, and c is 25. So the discriminant in this case would equal 6 squared minus 4 multiplied by 1 multiplied by 25, which is equal to 36 minus 100, which is minus 64. And as the discriminant is a negative number, we know that the original quadratic equation must have complex roots. The first method to find the roots of the equation is by using the quadratic formula stated here. By substituting our values for a, b b, and c, we can find our roots. We know that b is equal to 6, so we can say that minus 6 plus or minus the square root of our discriminant, which we worked out over here as negative 64, over 2 multiplied by 1, which is just 2. Now if you put this straight into your calculator, you'll find that you receive a math error because our calculators can't determine the square root of a negative number. So we're going to have to do this in our heads. Thankfully, this question isn't too hard. If we evaluate this, we get minus 6 plus or minus 8i over 2. And we can simplify this as 2 goes into all our terms, which means that our final roots are minus 3 plus or minus 4i. Another way we can work this out is by completing the square. In this example, we halved the coefficient of z and put it over here and made both of these equations equal to each other. The last thing we need to do to find the roots of our quadratic equation is rearranging for z. By moving the 16 to the other side, we can get that z plus 3 squared is minus 16, and by taking the square root of both sides, we get z plus 3 is equal to the square root of negative 16. We know that the square root of negative 16 is 4i. However, remember that when you take the square root of any number, the result can be both positive and negative. So in this case, we get that z plus 3 is equal to plus or minus 4i. And by moving the 3 to the other side, we get that z is equal to minus 3 plus or minus 4i, which is the same answer we get when we use the quadratic equation. As you may have realized, I haven't yet talked about dividing complex numbers, and that is because we first need to explore the concept of complex conjugates. Now this is a really simple concept which states that if we have a complex number z, which is equal to a plus bi, the complex conjugate of z, denoted by z with an asterisk at the end of it, is equal to a minus bi. All we're doing to get from the complex number to its conjugate is switching the sign before the imaginary part of the complex number. Now there are certain facts which may prove useful at some point during the course, the first one being that if you add a complex number and its corresponding complex conjugate, you'll get a plus bi plus a minus bi, which is just equal to 2a. In other words, you'll get double the real part of any of the complex numbers. If you were to multiply these complex numbers together, you would get a plus bi multiplied by a minus bi, and as you can see, this is the difference of two squares, which means we would get a squared minus bi all squared. Now if we simplify this, we get that a squared minus b squared I squared. However, we know that I squared is equal to negative 1, and these two negatives will cancel out, so we end up with a squared plus b squared. We can use this fact to divide complex numbers by each other, so let's work through an example on this. If we were asked to work out what 7 plus 3i over 4 minus 2i evaluates to, what we would do is multiply both the top and the bottom of the fraction by the complex conjugate of the denominator. So in this case, we'd multiply by 4 plus 2i over 4 plus 2i. Now note that we aren't actually changing the fraction, as this part only evaluates to 1, which is similar to rationalizing the denominator with surds. Now we can put this all together and say that's 7 plus 3i multiplied by 4 plus 2i over 4 minus 2i multiplied by 4 plus 2i. If we evaluate this, we expand the top to say that 7 times 4 is 28, 3i multiplied by 4 is 12i, 7 multiplied by 2i is 14i, and 3i multiplied by 2i is 6i squared, which is minus 6. Now to evaluate the bottom, we can actually use the trick up here, where a is equal to 4 and b is equal to 2. 4 squared plus 2 squared is equal to 16 plus 4, which is equal to 20. To finish off this question, we get that 28 minus 6, which is 22, plus 26i over 20 is our final answer. However, it is good to simplify your answer whenever possible, So in this case, if you plug this into your calculator, we can get that it is equal to 1.1 plus 1.3i. Another way to use complex conjugates to your advantage is by using the fact that complex roots will always occur in complex conjugate pairs. In other words, if we had a quadratic equation with complex roots of the form az squared plus bz plus c is equal to 0, and we were given one of the roots as being a plus bi, we can then work out the other root to be the complex conjugate of the first root. In other words, it would be a minus bi. You may be asked to find the quadratic equation associated with a given complex root. Let's say you were given a root of a complex number, 6 plus 3i, and you were told that the equation was quadratic. Using complex conjugates, we know that the other root of the quadratic equation must be 6 minus 3i, as complex roots always occur in complex conjugate pairs. We know that if these complex numbers are roots of the equation, subtracting the complex number from z would give you a factor of the equation. So our quadratic equation will equal z minus 6 plus 3i multiplied by z minus 6 minus 3i. Now if we expand this and simplify it, we'd get our final quadratic equation. So z minus 6 minus 3i multiplied by z minus 6 plus 3i is equal to z squared minus 6z minus 3zi minus 6z plus 36 plus 18i plus 3zi minus 18i minus 9i squared, which is also equal to plus 9. We know that the 3zi and the minus 3zi cancel each other out. We know that the 18i and the minus 18i cancel each other out. So we're left with z squared minus 12z plus 36 plus 9, which is plus 45. And this is our final quadratic equation. This rule applies to all kinds of polynomials, not just the quadratic kind. If we had a cubic equation of the form az cubed plus bz squared plus cz plus d is equal to 0, we'd know that the roots were one of two things. It could either have 3 real roots, or it could have 1 real root as well as 2 complex roots. This is because it's not possible for any equation to have just 1 complex root, as we know that complex roots must always occur in complex conjugate pairs. Alright, so that's pretty much all the content in complex numbers for Core Pure 1, but remember that we do go further into this in later chapters of both Core Pure 1 and Core Pure 2. Well done for getting this far if you did, and be sure to like the video if this did help you, and I'll see you guys in the next video.